Hi everyone, welcome to the algorithm seminar. Today we're very happy to have Rozhon to give a talk here. He's a PhD student at ETH Zurich, advised by Mohsen Ghaffari. He works mostly on distributed and parallel algorithms. He also creates YouTube videos about algorithms, channel name Polylog. You actually check this, seems much more popular than the channel of algorithm seminar.
Check what? Yeah.
Yeah. He has a young child and does no hobbies. Please welcome our speaker.
Okay, so hello everybody. Okay, hello everybody. So I will talk about k-means, and this is a joint work with these amazing co-authors. So Christoph is also here. Okay, so I will talk about this algorithm called greedy k-means ++. So in the first part of the talk, I will try to introduce this algorithm. And so this greedy k-means ++ is like a less well-known cousin of a well-known algorithm called k-means ++. And so I will really try to, mainly in this talk, explain like what is the difference between these two algorithms. And then I will maybe tell you something about how we analyzed this greedy k-means ++ algorithm, if time allows. Okay. So I think like the k-means problem probably doesn't need an introduction, but like the k-means problem, you got a bunch of points, right? And you want to find k center C so that you minimize the sum of square cost. These red centers, this is kind of the solution to this blue point instance. And of course, like why you are trying to find these k centers, because you try to find some kind of clustering, right? So, I assume everybody here knows what k-means is. It's like an amazingly important problem, both in theory and practice, right? So there is like this huge amount of theory. Like we know that, the problem is NP-complete, but even hard to approximate. On the other hand, there are many good approximation algorithms. Like the current record is probably something like just below 6. There is PTAS if you have fixed k or fixed dimension if you are in Euclidean space. And kind of the list goes on, and there are so many theoretical results. But somehow, as far as I know, like in practice, what's really important is just this like simple heuristic called Lloyd's algorithm, or like a special case of EM's algorithm, which really, just start with arbitrary solution, and then you are kind of incrementally improving until you are in some local optima. And so what I'm really interested in is like this intersection of theory and practice. And there is one very nice algorithm there called k-means ++ by Arthur and Vassilvitskii. So let me describe this algorithm now. So first of all, why is it in the intersection? Well, in practice, this k-means ++ is used as kind of the seed or like the initial solution for Lloyd's algorithm. So you can start this Lloyd's algorithm from like arbitrary solution. Maybe sometimes you start it just from like random solution, you take random k points. But like in practice, it is much better to start by initialize it with this k-means ++ algorithm. But what is nice on this k-means ++ is that it also has some nice theoretical guarantees. It is local approximation algorithm, which is like far worse, or it's like much worse than these best theoretical algorithms that can achieve constant approximation guarantee. But it is still decent. Like log k, it is still not so bad. So here is how this algorithm works. It's a randomized algorithm, and it constructs this set of k red centers in k steps. In the first step, you just take a random blue point. Okay, so first center, you just take it uniformly at random. So that's very simple. But here is what comes next. So for the next k-1 centers, you always sample a point proportional to its current cost. So let me explain what this means. So what is a cost? So if you have this point x, the closest red center is this center C. So then I say that kind of like the cost of x is square distance to C. Okay, this is like what I'm kind of currently paying for this point x. And sampling proportional to current cost just means you sample each point x proportionally to d of x to C. Okay, so this is what happens somehow in this first step, or when you sample the second center. You sample like proportionally to distance, which means that like these points that are kind of far away from C, they have like better probability to be sampled, right? Whereas these points that are very close to C, they have small probability of being sampled, right? So it's kind of like doing what we want. We don't want to sample points that are very close to C. So, maybe the next point that you sample is this red point. And then we are just iterating this thing. So when we want to sample the third point, we are again computing the cost of every point. So now it is a little bit more complicated because, for every point X, we need to kind of compute the distance to these two centers, pick the smaller one, square it, and this is kind of the current cost of X. This is what we are kind of currently paying for X in terms of our function that we want to optimize. And, we again just sample proportionally to the cost. So maybe this is the third point, and then we continue like this, right? So for example, here you see that I sampled the fourth point, and here I was kind of a bit unlucky because there is like this nice cluster, and I have sampled two centers from the same cluster, but this happens. So the life goes on, and now I have sampled all 5 centers, and the algorithm is finished. Okay, so somehow like the clusters that I have found, they would look like this. Okay, so somehow the clustering that I have found is not the best one, but it is a recent one. Okay. So now it's really important that we are all on the same page. So does this algorithm make sense? So this thing that I have put here, this is like the pseudocode of this algorithm, is the same thing, that's written in the maybe a different notation. So if it makes sense, can you smile at me or something? Yeah. Okay. Right. So it really goes back to this paper of Arthur and Vassilvitskii, who designed this algorithm and proved that it is locally approximate and this is tight. And if you go to Scikit-learn, let's see. If you go to Scikit-learn, like this popular Python library, you can literally see how they implement this algorithm here. Okay, so I really kind of like this, that we can actually really look at the code, right? And we can see that this is what they are implementing. Let me try to make it a bit bigger. Okay. Oof, that's too big. Okay, so you can, for example, here line 225, you can really see that this is like the for loop, right? Where you are kind of trying to sample each new point. But actually, if you are really looking at the Scikit-learn implementation, you will soon see that it is a little bit different. Like what they are doing there, it doesn't exactly match like the algorithm that I just explained. For example, here you see something like n local trials equal like roughly log k, and the clusters, this is like k. So when I explained this k-means plus plus, I never talked about something like that. There is some variable equal to log k. And they say this is what Arthur Vassilvitskii tried, but did not report specific results for other than mentioning in the conclusion that it helped. Okay, so something is happening here, right? What they implement is not actually k-means plus plus, and turns out that what is implemented in the Scikit-learn library is what is called greedy k-means plus plus. It's like a variant of k-means plus plus. So let me now explain what this variant is. Okay, so what is greedy k-means plus plus? So it's an algorithm which is very similar to k-means plus plus, but there is like an additional parameter that I call L. And basically what you are doing in every step is that instead of sampling just one new center, you actually sample like L candidate centers. Okay, and then there is some heuristic, and you use this heuristic to pick the best out of these L candidate centers. And this heuristic in this case is like the greedy heuristic, which means that you always try to take such a center so that the cost of the solution decreases the most. And now for each center, you can kind of put it in your solution. You can compute the new cost. So you just take the one where the cost is the smallest. Okay, so this is greedy k-means plus plus algorithm. Okay, so this will be some example for L equal to 2. The defined points, these are like the points that you have sampled. Right, and you can see that with this top point, we were kind of a bit unlucky, right? Because it's very close to a red center that we have already sampled. So what would happen in this algorithm is that like this bottom point would result in a bigger cost decrease, because this top point, this is not really decreasing the cost a lot, right? Because it's very close to this red center that we already have. So what this greedy algorithm would do is that it would pick this bottom point, which is kind of the thing that we want, right? We don't really want like these bad events where the new center is very close to an already existing center. So it's like some kind of heuristic that that makes the algorithm perform a little bit better in practice. And here again, this is again the algorithm just written in the maybe a little bit different notation. So the only interesting part is like lines 3, 4, and 5. So the line 3, this is again just the for loop. The line 4 is saying do the same thing as in k-means++, but sample L points, ci plus 1 up to ci plus L. These are like the new L points that you sample. And then the line 5 is saying pick the best point. And here pick the best point means you pick some like argmin so that the new cost kind of drops the most. Okay. So it's a little bit more complicated algorithm, but like still pretty simple to implement. Still very simple. Now the big question is, like, can we also analyze this algorithm theoretically, right? Because like k-means++, I mean, the nice thing on it is not only that it's practical, but we also have some kind of guarantees, right? And actually also like Arthur and Vassilvitskii, they were also the first in their paper who kind of tried this greedy heuristic. They recognized that it helps a bit, and they asked for its analysis.
What is it though?
So I think that what they tried was like L equal to 2, but then later there were some practical papers that recommended L equal to log k. So you should think about this L as being either a small constant or something like log k.
At some point it should get worse again, right?
Yeah. So Bernard had like a great observation. So like if you somehow think about L going to infinity, this algorithm will actually lose guarantees, because then it becomes just like the greedy thing that you always pick the
Yeah, and that's performs poorly.
Which performs poorly. I mean, yes. So like the k-means function is like submodular function. So if you are doing this kind of like greedy thing, you get some kind of guarantee like that the cost drops by constant factor, but this is like still very poor guarantee with respect to optimum. So yeah, it performs poorly. So for L going to infinity, this algorithm performs poorly. But now maybe the question is, what about L equal to 2? Okay. Let's say I sample just 2 points instead of 1 point. And now the question is what happens, right? So that's the approximation algorithm. What is the approximation ratio, right? And now we can actually even try to do some poll, right? I mean, maybe it's like still log k, right? It feels natural, like the original algorithm was log k. Now we sample 2 points instead of 1 point. Maybe it should still be log k, right? Or maybe it is slightly better. I mean, in practice, it seems to be just a little bit better. So maybe it is slightly better. It is also possible that we like totally destroyed something, and maybe we don't get any guarantee, right? So actually, do you have some opinions on it? Like we can do some kind of vote, right? So for example, who votes for this new algorithm to have complexity log k? Or sorry, like approximation ratio log k? Is there somebody who votes for it?
Well, what kind of
Okay, Exxon. Okay, thank you. So we have one vote here. So who vote for like little o of log k, like slightly better? Okay.
Optimistic.
isn't this like worse than normal k-means then, because your greediness?
Maybe it is. So you should then you should vote for omega of log k. Okay.
I feel like I know the answer, but I forget. So I'm gonna say none.
Okay, so who votes for none?
Okay, no, but you have some analysis of log k.
Yeah, is it omega log k?
Okay, so omega log k. Okay.
Yeah.
Okay, it feels like we.
Nail me down on what exactly.
Okay, I feel like we have like one vote for all the for every option. There is like exactly one vote. It feels like, but okay. So let's just go on. Yeah. So the first thing is that it actually cannot be little o of log k. It cannot be better than log k. And the reason is, I mean, I will not really like prove it formally, but basically the reason is something like this picture. If you have something like k very well separated cluster and kind of like 1 point in the middle, then this would actually be also like the bad instance for the original k-means++. In some sense, you could just kind of compute the probability of picking this point in the middle. If you compute all the probabilities, you get this log k, like omega log k approximation. Turns out it's also bad for this greedy algorithm. So this is a result by Bhattacharya, Euler, and Schmidt that says that this algorithm is omega L times log k approximate. Okay. So unfortunately,
This is how the parallel version of k-means++ works.
Okay, you mean k-means pipe?
Yeah.
This works a little bit differently. So I mean, partly yes. So in this parallel version, what you do is that you again like sample a batch of points, like from the distribution. But then in this parallel version, you just like leave all the points. You are not doing any like greedy picking, like
Sure.
pick one of them like cleverly. You just leave all of them, and then you are doing some kind of oversampling, right? That you do this like log n times. After these log n steps, you have like k log n points, and then you send it to one machine where you pick the best. Yeah, but this is like a great observation that is like very similar. In the sense, this is very similar to this parallel algorithm. Yeah. Okay, so
this one is still very sequential.
yeah, this one is still very sequential.
Yeah.
And
Because of
should
the
probably
groups.
do better because of that.
Yeah, this is very sequential algorithm. Yeah. Okay, so it's gonna be better, but you know, still maybe it is log k or maybe it is none, right? And it turns out that it is neither. It turns out that it's like log cube k. Okay, which like to me it seems like very random, or it's like very surprising, let's say, right? That it's actually log cube k
For
L equal to 2. For L equal to 2, it's log cube. Okay. And in general, so we have like this analysis that it is L cube times log cube k. So it depends on L, but like very mildly, right? If L is like log k, then it is still like polylog. And then we have like this almost matching lower bound, only almost because we lose like log k, like double logarithmic factor. Okay, but it's basically like L cube times log cube k. So it's like, okay, or if you plug in L equal to 2, it is log cube. If you plug in L equal to log k, which is what happens in the Scikit-learn library, you actually get log to the 6.
I like this idea of putting below the term you don't like in smaller.
No, it doesn't really negligible for all existing values.
Yeah, it is
No, I
like,
agree. I agree for that.
yeah. So you know, like the next time that you are using like this Scikit-learn library, now you know that you are using algorithm which is like log to the 6 of k approximate, right? It's like basically theta log to the 6 of k, which I find it like very so random that it's kind of interesting, I guess. Right. Okay. So this was the algorithm. So does the algorithm make sense? Can you again, you know, either smile at me or you know, say something like if it makes sense? Okay. Okay. So I will now go on, and basically like the main thing that I would really like to explain is like what is the difference, right? What is kind of the new dynamics that can happen even for L equal to 2, right? Why can't we just like recycle this analysis of k-means plus plus from Arthur and Vassilvitskii, and you know, why aren't we just done, right? Okay, so if I want to do this, then I first need to explain at least like one thing about this k-means plus plus algorithm. So I want to explain what is, at least for me, some kind of like the main lemma that you need to analyze this k-means plus plus algorithm. And it's kind of this lemma like that. Without this lemma, it feels like I wouldn't know like where to start analyzing this algorithm. After this lemma, I hope that it will look like, you know, you see like where the analysis could be heading. Okay, so this is the lemma statement, but I will try to kind of say it in my own words instead of, you know, trying to read this horrible formula. So, you know, suppose that we are somehow like in the middle of the algorithm, right? Like, for example, we have sampled these 2 red centers already, and now we are going to sample the first center, okay? And now let's say that I kind of condition that the third center is sampled from this optimal cluster K, okay? So I tell you that it is sampled somewhere from this cluster, but, you know, it is, I still don't tell you like which point is sampled as the center, okay? So basically, I take this distribution proportional to cost, and I restrict it to just this one optimal cluster. And now what this lemma is saying is that after I sample the new red point from this cluster, from this distribution proportional to cost, I can prove that the expected cost of this cluster is comparable with the optimal cost up to some 8 factor, up to constant factor. Okay, so this is what this horrible formula is saying. Kind of like this left side is like the expectation of the cost of the cluster. When I say cost of the cluster, I mean I go through all of its points. For every point, I look at the closest red center, square it. You know, this is like the cost of that point. I sum it over the whole cluster. This is kind of the cost of the cluster. And I say it's comparable with the optimal cost. Here I'm using this mu. This mu is like the center of mass. So this is like a fact about k-means that if you give me like one optimal cluster, the optimal thing where you put the center is the center of mass. So this is kind of the optimal cost. Okay. So I'm saying that like in expectation you are good. I mean, there is some proof of this lemma. It's not so hard. Like basically the proof is that first, if you sampled from uniform distribution, then it wouldn't be so hard to see it. You would just, write down the algebra, and it wouldn't be so hard. In general, we are not sampling from uniform distribution, but there are like two cases. So either all of these red centers we have already sampled, they are like very far away, and then we are sampling basically from uniform distribution, so everything is fine. Or if we are not close to uniform distribution, it actually has to mean that there exists at least one red center which is very close. But if there exists one red center which is very close, we don't even need to sample the new center. We already know that we are good in the cost. Okay, so basically the proof reduces to prove it for uniform distribution, and that's like not so complicated. But here is how I want you to think about this lemma. I mean, this lemma is really great because, forget kind of this expectation, forget this 8 approximation. What it is saying is that, like, once I tell you, like, which optimal cluster I hit with the next center, you can kind of, like, tick it off, right? You can say, oh, yes, this cluster is going to be fine, right? This is, like, what this lemma is saying. You kind of want to be comparable with opt cluster, and this is saying, like, whenever I hit some optimal cluster, I can tick it off. I'm competitive with optimal, right? So this is like this amazing feature, and like once you have this lemma, then basically the rest of the analysis is just about trying to argue about the probability that you hit the same cluster twice.
So this is some kind of coupon collector.
Exactly. The analysis looks in the end very similar to some coupon collector. There is some harmonic series that sums up to log k. Okay. So basically the rest of the analysis is really just, you need to be carefully write down all the formulas, and then it just like works out. Okay. So this is how you would analyze k-means plus plus. Like with this lemma, it's actually not so difficult to finish the analysis. Okay. So this was something regarding k-means plus plus, but now let's go back to greedy k-means plus plus, right? Now I want to like explain what is the difference, right? Like why it is not so simple. And to do this, let's actually change the algorithm a little bit, or actually maybe generalize it a little bit. So, when I told you this algorithm, it was not a priori clear if this greedy heuristic is actually useful for something, right? Maybe it is the case that like whenever you sample L points, and then you pick like arbitrary one of these L points, you can't make it so bad, right? Maybe like one way to analyze this greedy k-means plus plus would be forget the greedy heuristic, just say that, we take like one adversarial center out of these L centers, and it is plausible that such an algorithm could still be like good approximation, right? So it turns out that this algorithm actually is very bad. Okay, it turns out that we really need to rely on this greedy rule, and if you don't give me this greedy rule, if you just plug in like any rule or adversarial rule, the algorithm is basically like omega k approximate. Okay, so omega k is like really bad. And here is the instance like where this thing could happen. So I will not really tell you like exact like properties of this instance, like what are the distances between points and so on. But basically there is like one very big cluster in the middle, and then there are like k-1 clusters on the outskirts. Okay, so this would be like the optimal solution. You just take the big cluster in the middle, and you take these k-1 clusters that are very far away. And also, let's say that's kind of like this cluster in the middle has like roughly as many points as all of these other clusters outside. Okay. And now let's say that L is equal to 2 or some small constant. And let's try to see like what the greedy algorithm, or sorry, not the greedy algorithm, but kind of like this adversarial algorithm, how it could look like, what can happen, right? So maybe you sample the first 2 points. And because kind of there are roughly as many points inside as outside, maybe like 1 point lands inside, like the steal point, and 1 point land on the outside. Okay. And now, of course, we can use our lemma, right? So this is this lemma that we discussed, which says that like an expectation, the steal point in the inside cluster, it will be like roughly in the middle. It will kind of give us like 8 approximation of optimum. The steal point on the outside is also going to give us like good approximation of optimum. So basically, it sounds like we are in some kind of like win-win situation, right? Whatever cluster the adversary picks, this cluster is going to be well approximated, right? So I will now play the adversary, and I will say, and And I will say, okay, so do you have suggestions like which cluster I should center? Okay, I will actually pick the top point. Okay, I will pick the top point, which means that now like this top cluster, this very small cluster, it is very well approximated exactly as the lemma guarantees, right? Okay, the game goes on. Okay, the game goes on, and again I sample the next 2 points, right? Again, one of those points is like from this middle cluster, and the next point is like again one like from one of these like clusters on the outskirts. Now it is this right cluster. Okay, again I can apply this great lemma from Arthur and Vassilvitskii, and this lemma is again telling me that I'm in some sense in a win-win situation. Like whatever cluster I pick, I mean in expectation, I'm going to be good, right? Okay, so again I will play the adversary. I will pick the small cluster. Okay, and the process goes on. Now this thing happens. Oh, now this is really bad because look at what happens, right? The algorithm sampled this point, which is very far from the center of the big cluster. And now if I take this point, I will actually, it will be like horrible approximation of this middle cluster. So why can it happen? Like, I mean, I have this great lemma, which is telling me that I'm always at approximation in expectation. So why can it happen? Well, it can happen because this lemma is only in expectation. It is not like deterministic guarantee, right? And the kind of the best I can say is like some kind of Markov inequality, which says like that if expectation of some random variable is 1, and then, you know, if I sample it 100 times, then the best thing that Markov inequality can tell me is that it will never be larger than 100, right? But I mean, if this is the best thing that I can prove, it means that if I'm kind of playing this game for k steps, and each step I have like a good expectation, it means that there may be one step where I'm actually k times worse than expectation, right? It's like some kind of like anti-Markov inequality, or like, you know, if Markov inequality is the best thing that you can do, then this thing can happen. And if I'm the adversary, I will basically like wait for this one bad event. And when this bad event like happens, I will totally take this middle cluster, right? And then I kind of don't care what happens next in this algorithm, because in the end, I will just be k approximation. So that's pretty bad. Okay. So this kind of proves this like omega k lower bound. I mean, if you look here, actually this is only like k to the 1 minus 1 over L. So this lower bound would only work if like L is log k. Because if L is only 2, then actually with constant probability, both of the points will be in the middle. And then I cannot like play this adversary, right? But if L is log k, or if you change the numbers a little bit, then you get lower bound. Okay, so what is the lesson of this thing? The lesson is that actually this greedy rule is really important, right? I mean, without this greedy rule, we are just completely screwed. And it also tells us like what's the new thing that we kind of need to analyze, right? I mean, this process is really more complicated than for L equal to 1, which was analyzed by Arthur and Vassilvitskii, because even for L equal to 2, we have like this completely new thing that can happen that cannot happen in the original algorithm. Okay, so let's now maybe think about this greedy algorithm. So what would happen if we run this greedy algorithm on this instance, right? Maybe this greedy algorithm can also fail on some instance like this. But actually, you cannot really like tweak this instance and construct like very bad counterexample to greedy k-means ++, because you know what this greedy rule is doing, or you know like whenever it happens that the greedy samples 1 point from this middle cluster and 1 point from this very small cluster on the outskirts, the greedy will like really want to take this cluster in the middle, right? Because this cluster in the middle is like k times larger than the clusters on the outskirts. So it's like k times bigger cost drop, right? Because the cost basically drops to 0. Because like originally for every point we paid something very large, now we will pay like almost 0. So the cost drops like much better if we pick the point in this inside cluster. So yeah, so this argument doesn't work for greedy k-means ++. And okay, so here is how we kind of analyze this greedy k-means ++ algorithm. So this is like the main technical lemma that we prove. So what we prove is that like whenever you fix one optimal cluster, then we can actually say that there is only like polylog k, only very few number of centers that are sampled from this cluster during this whole sampling process, okay, by this greedy k-means plus algorithm. I mean, technically it's like a little bit more complicated because somehow we are not counting the points throughout the whole algorithm. We are only counting the points until, let's say, the cluster becomes covered. When I say it becomes covered, it just means that like one point is really like taken by the algorithm, because like once, in some sense, the algorithm takes at least one center from an optimal cluster, I don't really need to think about this cluster anymore. I kind of don't care about this cluster anymore. Okay. So but you know what, like the main message is that like what the lemma is saying is that like if you fix any particular cluster, then it cannot happen that you sample many points from this cluster. And if we now kind of go back to this bad instance, like this is exactly what was kind of killing us, right? What was killing us was that we had like this one cluster, and like k times it happened that we sampled from this cluster and that then we didn't take the center. This was like this bad thing, right? Like we sample, we don't take it. We sample, we don't take it. And we are waiting until this like one bad point. And basically, okay, if I again now go back, so if you now put everything together, then you get like this L cube times log cube k approximation factor that I said in the beginning we can prove. And basically it works like this, like from this original k-means plus analysis, we inherit this log k. This new algorithm still has it. Then we also lose like additional factor of L. This is basically because, you know, in this original k-means plus there was like this problem that like what happens if we sample a point from a cluster that is already covered, where we already have a center. And now this event has like L times higher probability. And finally, what's kind of the most important is that we also kind of use this lemma, which says that like from every cluster we sample only a few number of points, which means that we can kind of use this like Markov inequality to tell us that even if you look at all of the points that we sampled from this cluster and you kind of take the worst one, even this worst point is not that bad. And kind of putting it all together gives us the analysis. Okay, and then you can also construct some matching lower bound, because basically like every partial argument to like in this upper bound analysis is in some sense tight. So then you just need to find some kind of picture that combines all of these like tight instances for all of the arguments. Okay. So this was like the second part of the talk, where I tried to like explain what is really the difference between this normal k-means plus and this greedy. What is like the new thing that can happen there? So does it make sense? Are there any questions?
So everything is tied up to this low order log
factor. Yeah. So this low order log factor, we didn't think about it like so much.
I know.
Basically, like roughly speaking, like where it is coming from is that like in this lower bound, we are making only statements like, how does it work? So you know, you should imagine something like that. The algorithm has like some kind of like loop that like, or that there's like sequence of log k things that happen. And like for each one of them, we would normally prove only like that with 99% probability. What we want to happen happens. We need concentration of log k. This is it.
No, but all the like the log cube is tied. Everything is tied up to the log.
Exactly. Yeah. Okay. Yep. So any more questions? Okay.
So I mean, given this, is there, I mean, better heuristics that?
Yeah, this is a great question.
Like example 2L, and let's take the most spread out L points.
Yeah, I think this is a really great question. In some sense, if you use like the opt heuristic, like let's say you sample L, let's say that L is like log k. So you sample log k, and then you use like some kind of like optimum like oracle in some sense that like tells you like how to sample the optimum point. You can prove that the constant factor goes down to 0.1. Okay, so once you sample like log k points, there exists a certain heuristic with which the algorithm really is like constant approximation. Okay, but this heuristic is not something simple. It's something like, you know, exponentially complicated. Or it's not something like, if I know how the solution looks like how the optimum solution looks like, I can point at this particular center that you need to pick, right? I of course don't know this thing, right? So I'm saying this thing because like, Yes, I mean that should be something, right?
But if the main thing that happens is double coverage or kind of large clusters don't get covered, or double coverage, then. But you haven't played around with.
We didn't find anything that worked. But I think this is like really interesting to look at, right? Because this is like practical algorithm, right? Like people use it in like Scikit-learn. Maybe if you like do like something again like very simple but a little bit different than greedy heuristic, maybe it would be possible to analyze it, and then maybe it's like again like 10% better than the current thing, right? So I think it makes a lot of sense to look at this. Yeah, so any more questions? Okay, great, so we can go on. Yeah, so I actually kind of assumed that now it will be already probably the end of the talk, but since it isn't, let's try to explain a bit about this log square k, right? Like where is it coming from? And it gets a bit complicated, okay? So, but let's try it, okay? So this is the picture that I want you to like have in mind. So here in the corner we have like this cluster K, and this is the cluster for which we want to prove that we sample only a few centers from it. Okay, like the thing that I now want to prove is that like from this cluster K, I sample only like polylog K centers like throughout the algorithm. And for this cluster K, like one interesting point to look at is like the closest thread sample which is already sampled. Let's say this is like this one. Okay. And let me also now make some kind of simplifying assumption that says like that there are like no other points in this ball. Okay, I like look at the center of K, look at the radius to the closest red point. Let's say there is nothing else than the cluster K. So it's like very well separated, right? You have like this cluster K, then there is like this one red center, and then somehow the rest of the points it lies like somewhere outside. Okay, so this is like the rest of X. Okay, so this is kind of the picture that I will now try to analyze. I will kind of try to persuade you that there is only a few number of points that we sample from K. Okay, so first of all, kind of without loss of generality, we can assume that kind of the cost of this cluster K and the cost of everything else is like roughly the same up to K factor. So why is it? Well, if the cost of everything else is more than K times large than the cost of the cluster, then, like in the next step, when we sample the next center, by the way, also let's say that L is equal to 2, that we always sample just 2 centers. So when we sample them, like with overwhelming probability, they will be sampled from this X without K, right? So during like this K step, when the algorithm is doing something, like the probability that we sample from K is kind of negligible, right? So we can really assume that this cost of X without K isn't like so much larger than the cost of K. Also, if it ever happened that the cost of like rest X without K becomes like super small, then again, like both of the points that we sample them from K and we finish the algorithm, right? So it's all kind of like related up to this K factor. Okay. So
why is it a K factor on the second argument? Not a.
Yeah, it's maybe even constant. Yeah, it's maybe even constant. Yeah, it's probably just a constant.
Okay.
I can actually like poly K is enough for my argument. Okay, and here is a little bit more subtle thing. So let's say that, I mean, I look at one point of this X without K, okay, maybe like this point. And I kind of ask you the following question. So if you add this point to the set of centers, how much the cost drops? Okay. So I kind of claim that without loss of generality, I can assume that for like most of these points, or let's say even all of these points, if we put this point into our set of centers, the cost of our solution drops at least as what is the cost of the cluster K. And why is it? Well, imagine that it wouldn't be true. Imagine that there would be like a lot of points here, such that if you kind of put this point into your solution, the resulting cost drop wouldn't be like so drastic as the cost of K. Well, then whenever it happens that we sample 2 points and one of them is this point and the other point is somewhere in K, then actually, if we put this other point that is sampled from K into our solution, the cost will really drop by basically cost k, because currently we are paying cost of k for this cluster k. But if we take like basically any point out of it to our set of centers, the cost drops like so drastically. It basically like drops to 0. So like originally we paid like cost of k for this cluster, and now we pay basically 0. So it's like this very big drop if we take any points from k. So we kind of can assume that also like any point outside of k will also result in a big cost drop. Okay, so this is basically like the models of generality. Okay, and now finally here comes like the argument. So like imagine what is now happening, right? So we are basically like sampling all of these points, and let's say at the beginning the cost of this x without k is like k times larger than cost of k. It is like really large. So like most of the points that we are sampling are from this x without k, right? And whenever we sample a point, we also like take it, and the cost drops by a lot, right? It drops by like basically cost of k. And now like what I claim is that if you are waiting, if you wait until the cost of x without k drops by 2 factor, then like during this time in expectation we sample roughly like 1 point from k. So maybe the way to think about it is like if the cost of k is like 1 and the cost of x without k is 100, then it means that like in every step you have like 1% probability that you sample from k, right? So you have like 1% probability that you sample from k, which means that like roughly after like, I don't know, like 50 steps, you have like constant probability that you sample from k. So in expectation you sample like 1 point. But also because each time you don't sample from k, the cost drops by 1. You know that after 50 centers that you sample, the cost drops from 100 to 50. So this is like, okay. So basically, if you like write down all the formulas, you get that somehow for every 1 point that you sample from k, the cost in the outside drops by 2 factor.
So where does the second log k come from?
Okay, so again, Bernard is like 1 step ahead because this thing would give log k, right? And we would be done, except we did this thing with loss of generality. So I kind of said, assume that there are no points here, kind of in this big circle that would be somehow closer to the cluster k than this closest center. Okay, so this was actually the loss of generality. And here is how the full picture looks like. And now I will wave my hands even more. Okay, so if you don't get it, then you know nothing, it doesn't matter. So the next picture you should have in mind is like picture like this, where I have also added some junk here. Okay, so these are like some junk blue points from different clusters. And now let's again try to see what's happening. And let's make this assumption that like the number of points in the junk is smaller than the size of the cluster. I can make this assumption because in some sense, if there are really a lot of points in the junk, then it's kind of good for me because it means that whenever I sample a point from this junk and k, I probably sample it from junk and not from k. So I can kind of assume that this junk is not so much larger compared with the size of the cluster k. And now, like the original argument that we made was that, you know, the original argument kind of finished by saying, sure, we have to sample something from k. But now instead of this thing, like it says, we sample like log k things from k. But now we again sample like log k centers. But you know, some of these centers are from k and some of these centers are from junk, right? So basically what happens is that we can say that, okay, we have sampled log k centers from here. Some of them were in k, some of them were in junk. And one of these centers, like in the end, one of these centers like was really picked. So these are all like sign points that were considered. There's like log k sign points. And basically the argument of the previous slides tells you that one of these sign points was picked as the center. And somehow what is like the worst case that can happen? So even in this worst case, when this sign point when like this point was picked as the next cluster, then, well, we are still not done because this red point is still not in k. So somehow the argument is still not finished. But somehow what we know is that like in expectation, there is like roughly 1 over log k fraction of junk that goes out.
Right.
Right, because if you imagine this junk as kind of, if you put it like on a scale of how far is it from k, okay, it's kind of going farther and farther, and you have like, you know, t random points out of junk. It means that even the farthest point of junk there is still like 1 over t fraction of junk after it, right? So basically, in the end, what we say is that like 1 over log k fraction of junk goes out, which means that like after log k iteration of this, all junk is out. And then we finally can apply previous slide and say we sample from k. So if you didn't get this, then, doesn't matter. It's just like there is some kind of like double for loop that's happening in this.
And that's where the L squared thing comes from.
So currently this is for L equal to 2. If L is general, I mean, you just do the same set of calculations. And you get L squared also. Okay. Yeah. So you get like, instead of 1 over log k, you get like 1 over L log k and so on. Okay, so let me try to see some kind of summary. So this is this greedy k-means plus algorithm. It's like extremely simple algorithm, right? Especially if you compare this algorithm with the previous 2 slides, which showed like some actually pretty subtle thing that was going on. So this is like extremely simple algorithm, right? It's used in this Scikit-learn library, so it's also pretty practical. And yeah, somehow like what we proved is that this algorithm is still well behaved, in the sense that you cannot construct some instance where it would totally break. And yeah, I view it actually as a small miracle that it is well behaved, because the analysis is quite subtle. For example, there is one thing that I didn't tell you, but actually the fact that the heuristic is greedy and not something else, we actually use it crucially on 2 different places in the analysis. So I was kind of talking about like one place in the analysis, but it is really crucial that the heuristic is greedy and not something else. But there is actually a totally different place in the analysis where we again need to use it in like totally different context. So it's actually I'm still a bit surprised that like everything still works. And maybe you can try to view this result as some kind of like theoretical justification for the greedy rule, right? Because you can have like a lot of heuristics that you could put here instead of the greedy rule. But I think that for most of them, this analysis wouldn't go through, right? If you really have like these 2 different places in the argument where you kind of use it quite.
Do you think the algorithm wouldn't work or the analysis?
The analysis wouldn't work. I mean, in practice, yeah, probably it would
no,
work.
but I mean, theoretically.
Yeah, I think like.
Loses property.
Yeah, what I'm claiming is that if you replace this line 5, and instead of argument of something like that, you pick the point where the cost drops the most, I say you pick something reasonable looking, it will probably not work, like the analysis.
But my question is, the analysis will not work, or do you think
Worst case guarantee?
Worst case guarantee. I'm saying, yeah, I'm saying not only our analysis will not work, but I'm saying like, it will probably be like omega k.
Okay, got
approximation. Yeah, this is what I want to say.
But is there anything in here that explains or suggests or
like a better rule
that it actually or I mean we do it because it's better empirically.
Yeah.
And everything that we do here is so far it's not too much work.
Yeah, exactly. This is like the downside,
Exactly.
right? I mean, this analysis
Exactly
is
the same thing.
yeah, totally. Yeah, this is like a downside of this thing, right? So like like probably like why it is better is like exactly this intuition, like from the like very beginning of this talk, where we saw like in K-means plus plus it can happen that you have like one nice optimal cluster and you sample 2 samples from it, right? And this thing like will happen in K-means plus plus, and in this greedy rule, it's like more spread out, right? It's
So
just a little bit more
maybe
spread out.
the intuition is that if you have something that's decently well clustered, then this will perform better.
Maybe, but then again, like, again, if I go back to the beginning of the talk, I mean, there was like this example with this one point in the middle. So where is it? This one. So this is like this is like a nice instance in the sense that you have like, k clusters plus 1 outlier point. Everything is very well spread out. And, this is omega log k for K-means plus plus and omega L times log k for greedy K-means plus plus. Because basically the only reason why this is bad for the algorithm is this one point in the middle, which is, this is like this poisonous point. Once you take it, you are screwed, right? Because once you like allocate one red point for this guy, you cannot allocate it for one true cluster, and you pay a lot. And
but something is special about this point, right? Because it's not clear that greedy would. I mean, in this case, the point is special that it's gonna be picked by greedy. Right? If the outlier was actually an outlier and it'd be far away, it would actually probably not be picked at all, right? I mean, Like
Yeah,
take something that's nicely clustered and you add a few random outliers.
Yeah,
This
that would
effect
make more
will not
sense.
happen, right?
Yeah, that's a good point. Yeah, it's really important that this like outlier is actually not really outlier.
Yeah,
It's
not really
actually
an outlier.
kind of like a grain point, right? I mean, I can really like feel it in my heart. Like
It's
I
the
understand
optimal-
greedy why it wants
the
to take it.
optimal solution for like, well, one cluster more or a couple of clusters
Yeah.
less, right?
Yeah. If like k is equal to 1, actually optimum would be to take this thing, right? Or if instead of k I allow you to use k plus 1, then again like this doesn't go through. So
it's not really
Yeah.
a noised, nicely clustered instance.
that's good point. Very good point. Yeah, so perhaps there could be some kind of analysis that actually shows that it's maybe even better in some way than K-means plus plus.
Cool.
Kind of the only thing we are proving is that it's not much worse. Okay. Yeah.
Well, I mean, it would be surprising if you can do something that's actually little overflow k in the worst case. By just, like sequential
maybe
taking
better
things
rule,
without some heavy computations.
There is actually an algorithm of Latanzi and Zoller, which actually kind of combines this K-means plus plus idea with local search. And what they do is that they first run K-means plus plus, but then like for additional K steps, what they do is that they kind of sample K plus first point, okay, again from the same distribution, and then they look at all of the K plus 1 points and kind of they take out the one which like greedily is the best to take out, meaning that the cost increases the least. And if you do this thing for K steps, then you can prove that you get constant approximation. So if you kind of like combine this K-means plus plus with this like local search, then you can actually get constant approximation.
You need just k more steps, right?
And you need K more steps. Yeah.
Cool.
Yeah. Okay. So thank you.